There are three stages to aerobic energy system, and these are aerobic glycolysis, Krebs cycle, and the electron transport chain. Stage 1, aerobic glycolysis. If there is no PC available, there will be a buildup of ADP. This buildup of ADP creates PFK, and this initiates the breakdown of glucose. Glucose is broken down by an enzyme called glycogen phosphorylase. This stimulates the creation of pyruvic acid, which allows a yield of 2 phosphates. There is oxygen available, and so pyruvic acid reacts with the enzyme coenzyme A to stimulate acetyl-CoA. 2 moles of phosphate are also created. Stage 2, Krebs cycle. Acetyl-CoA from stage 1 reacts with oxaloacetic acid to create citric acid. Citric acid is then used in the Krebs cycle, which gives us 4 products: oxaloacetic acid, so that the cycle can be redone, carbon dioxide, and 2 moles of phosphate and hydrogen. Stage 3, electron transport chain. The hydrogen from stage 2 binds with NAD and FAD to make NADH and FADH. It then goes along the electron transport chain and creates 2 different products. These are hydrogen ions, H+, and hydrogen electrons, H-. The hydrogen ions, H+, mix with oxygen and produce H2O, which is water, and 4 moles of phosphate. Meanwhile, the hydrogen electrons, H-, stimulate 30 moles of phosphate. Overall, ATP aerobic creates 38 moles of phosphate. ATP aerobic produces energy from 3 minutes up to 1 hour. For example, this will be used in a 10,000 meter race. Muscle spindles and Golgi tendons. Muscle spindles are proprioceptors, which are found within skeletal muscles. They detect muscle stretch and initiate a reflex that resists the stretch. Every time the muscle stretches, the muscle spindles respond and sends information to the spinal cord. Secondary sensors detect information about the degree of stretch and send this to the CNS, which is the central nervous system. The CNS then transmits information to the motor neuron for the muscle to reduce the stretch. The Golgi tendon organ is a proprioceptive sensory receptor organ which detects the tension of the muscle. Golgi tendon organs is located at the origin of the muscle fibers. As a muscle contracts and shortens, it increases tension within the tendon. When a Golgi tendon organ detects a level of tension too great that has the potential to cause harm, it sends a signal through the sensory neuron to the central nervous system, where the inhibitory interneuron is activated. This forces the muscle to relax and prevents tension increasing in the tendon. Both of these would be used in steady state exercise when the muscles contract and when the muscle is contracting too much. This is when the Golgi tendons would release the contraction and let the muscle relax to prevent injury. Breathing rate. During steady state exercise, breathing rate will increase as more oxygen is needed in the body, and so more air needs to be inhaled. It inhales more because there is an increase in the amount of peripheral feedback, and it sends a message to the DRG. The DRG then sends an impulse along the intercostal nerve to the external intercostal muscles, which then contract, and as a result of this, the diaphragm also contracts, increasing the size of the chest cavity. As there was an increase in the amount of peripheral feedback, the chest cavity space will increase rapidly, and that would mean the performer would need to breathe in a lot quicker and frequently. As the body inhales more, then it would also need to exhale more. It exhales because there is an increase in the amount of central feedback, and a message is sent to the VRG, which sends an impulse along the phrenic nerve to the internal intercostal muscles. They contract and decrease the chest cavity space rapidly, causing the performer to breathe out quicker. After this increase in breathing rate, it then plateaus as the body is able to get the amount of oxygen needed and so doesn't need to breathe in any faster. Mo Farah is an elite athlete and would have a lower breathing rate compared to the normal person, 12 to 20 breaths per minute. He would have a lower breathing rate as he would have a stronger respiratory system and wouldn't need to breathe in and out as much to still be able to get the oxygen he needs in his body. Reference is Pearson Schools and FE colleges. Tidal volume. Tidal volume is the normal volume of air displaced between normal inhalation and exhalation. During exercise, this will increase as the body needs to get rid of a lot more carbon dioxide and needs a lot more oxygen. If they need more oxygen to be breathed in and more carbon dioxide to be breathed out, the exhalation volume will increase, and so would inhalation volume, which would result in an increase in the higher tidal volume. The average tidal volume is 500 milliliters. However, an elite athlete who works in steady state exercise would have a higher tidal volume. This would be because they would use continuous training a lot, and as a result would have a stronger respiratory system than the average person. This would enable him to be able to take less breaths per minute. Therefore, he would need a higher tidal volume so he is able to take less breaths per minute but still get enough oxygen to be able to use his body normally and use all of his body systems. The same reference as before. Oxygen dissociation curve. The oxygen dissociation curve shows the relationship between the percentage of oxygen saturated of blood, a measure of oxygen dissolved or carried in blood, and the partial pressure of oxygen. During steady state exercise, increased temperature and lower blood pH contraction affect the oxygen hemoglobin dissociation curve, so that more oxygen can be unloaded to supply the active muscles. During steady state exercise, you will move to the right on the graph. This is because the hemoglobin would have a lower affinity for oxygen, meaning it would be harder to bind with, but will make it easier to let go of. This means more oxygen can be released at the muscles. Neuromuscular responses. Increased muscle pliability. According to Louis Sutton, 2010, ligaments and also tendons will increase in flexibility and strength with regular exercise. Athletes require stronger tendons and more pliable ligaments to handle the demands of the exercise. This warming of the muscle during activity makes them more pliable and reduces the chance of injury. This can be summarized by saying that during exercise, our tendons and ligaments being used are pliable, meaning that they can continue at the same duration and intensity. As we exercise, there will also be an increased amount of information sent to the central nervous system from the Golgi tendons. It is then the job of the Golgi tendons and muscle spindles to facilitate smooth movement patterns, and the heat increases the speed of the transmission involving the nerve impulses. These are the graphs that were made from the data of the O2 saturation of the 3 participants that took part in steady state. The estimation of O2 saturation would be an increase at the start of steady state exercise, as more oxygen is needed to get to the muscles. Then it would plateau as the muscles are getting the amount of oxygen they need in order to continue working at the same intensity. After the exercise, it would then drop fairly quickly as the steady state exercise supplies oxygen the whole time, and therefore the body doesn't need to rapidly inhale air to get the oxygen. From the results, we can see that the O2 saturation drops at around the 4-minute mark and then would follow the prediction of an increase in O2 saturation, followed by it plateauing off after around the 8-minute mark. This same pattern is the same in all three of the participants, and therefore there isn't any data which is an outlier, as all three of the participants had the same results, so they are all valid. The results taken from the groups titled Billy and Rachel are the most accurate compared to the nominative data. However, Billy had a slight drop after about 5 minutes, which isn't what would have been expected. Rachel is very close to the nominative data, however. It fluctuates towards the end, and this would preferably be straight in the nominative data. Heart rate. These are the graphs taken from the data on the heart rate of the three participants. Some of the results backed up the hypothesis that the heart rate would start off with a sharp increase and then eventually plateau off, before finally rapidly dropping after the exercise. Based off the results, there is an increase at the start of exercise, and it does level off after roughly the 8-minute mark until the end of the activity. However, in the results we collected, the heart rate plateaued off a bit before increasing again. In one set of results, Billy, the heart rate dropped again at the 12-minute mark. This bit of data can be discarded as it doesn't match the other groups' results or the nominative data. Out of all the groups, Luke was the group that had the results close to the nominative data, as there was a clear increase at the start, and the rest of the data is very similar to the results, as it almost plateaus. It would be more accurate if after the increase there was a straighter line as to where the results plateaued, instead of the heart rate continuing to slightly increase for the rest of the exercise. These are the graphs made from the data of the lactate of the three participants. Based off the results we have gathered from the lactate levels in the performers during steady state exercise, we can estimate that the lactate levels should decrease from 2-minute mark to the 6-minute mark. We can tell this because this happened in 2 of the groups and backs up the hypothesis that the lactate level will drop. From this point on, the graphs all go in different directions, so we are unable to come away with a precise analysis. However, it doesn't follow the nominative data, as there isn't a plateau present in any of the data graphs. Unfortunately, not enough groups managed to get enough results to make a graph on the blood pressure during the steady state activity, and so the blood pressure results aren't valid. Borg scale. From all of the results of the Borg scale, the nominative data is that it starts off with an increase before it plateaus and finally increases again. However, in one of the groups it decreases after the plateau, so this would be an anomaly, as the other 2 groups had a similar increase, which means that is more reliable than the one group that decreased again. Breathing rate. The data for the breathing rate is different for most of the groups. However, in all of the groups the breathing rate increases at the start of exercise. In one of the groups the breathing rate then slightly dips before carrying on to increase for the rest of the activity. However, for the other 2 groups, the breathing rate follows the hypothesis and plateaus before decreasing again afterwards. Before decreasing again afterwards. Based off this, we can say the nominative data from the test backed up our hypothesis. The graph of Luke's data shows the shape of what the hypothesis would look like, as it starts off with a sharp increase followed by a plateau and finally returning to normal after the activity. Luke's results is in the bottom left hand corner, so you can see what it should look like. Cardiovascular analysis.